Good morning, students, and I have already sent you some videos regarding the plant and molecular techniques, and we have also discussed before on the virtual class about this UV spectrophotometry. And today I will try to give an overview of the fluorescence spectrophotometry. But before I say something, if you remember the class of the microscopy, we have already discussed about the fluorescence. So keep that idea, what exactly is the fluorescence, luminescence, and the phosphorescence. This will try to take you further on. So if you look here, so we have already discussed before that for any spectrophotometry, so there is a light source, there is a sample, and so once the light is passed through the sample, there is an absorbance, transmittance, and detector. Now what we will do is, in addition to this, there are the certain compounds or the molecule which is present in the sample. They have the property of luminescence, and if you measure this, the phosphorescence or the luminescence, then this is called as the fluorescence. If you measure this, the fluorescence, then it is called as fluorescence spectrophotometry. So if you look here, so what is called there, I mean, it is simply called the spectrophotometry, and it is the kind of electromagnetic spectroscopy because it also measures the wavelength changes, and that analyzes the fluorescence from a sample. So imagine if we use a beam of ultraviolet light, so what will happen? It will excite the molecules present in the fluorescence and causes them to emit light, but not necessarily the visible light. And we have already discussed, so these are the different electromagnetic spectrums. So here, if you look here, this is the visible range. Before the visible is the UV, X-rays, the gamma, the IR, the microwave. And as the wavelength increases, if you see here, as the wavelength increases, the frequency, the energy decreases. It means if there is a lower wavelength, it has more energy. So normally in the case of the spectroscopy, this is also considered as the emission spectroscopy, because if you see here, this is the EVAR state, this is the EDU state. When any of these, the molecule are excited by these the high the energy light source, they can go to the higher energy state, and when they return back to the ground state, then there is a emission of light, and this is simply called as the fluorescence. And now if your sample have the capability or the capacity of this the emission of the fluorescence, and if you can detect this is simply called as the fluorescence spectrophotometry. So if you look here, so emission is a spectroscopy which examines the wavelength of the photon emitted by the molecules during their transition from an excited state to the lower energy state. So as I told you before, so this is simply called as the luminescence, the emission of light from any substance that occurs electrochemically from the excited state, and this is called as the fluorescence. Mostly it is 10 to the power 8 per second, and if it is the phosphorescence, is little bit slow, is around 10 power 3 to 10 per second. And therefore, normally in practice for the spectrophotometry, the fluorescence is the more widely used chemical analysis for phosphorescence. And if you look here, this is very important slides. So if you look here, just try to explain you. So this is the nucleus, and these are the different energy levels. So when there is excitation of high ultraviolet radiation, and therefore this guy moved to the higher state, and when it returned back to the lower state, then there is a release of energy, and this energy could be captured in the form of the fluorescence. So again is the process of the power of energy absorbed by the substance and released in the form of light, and therefore it is called as the fluorescence. Again, same story here. So this is the ground state S0, S1, when it reaches to the higher state, and when there is a release of energy, and again there is a release of fluorescence. So normally in the fluorescence spectrophotometry, we simply measure the emission of the fluorescence from a molecule present in the sample, and that is why it is called as the spectrophotometry. And I think I have already explained. So what does it do? So it simply analyzes the fluorescence from the sample. So what does it do? It involves the beam of light, same like in the normal spectrophotometry. Mostly it is ultraviolet because it is a high energy level that excites the electron within the compound, and then it causes them to emit the light. And the devices which measure these guys, these are called as the fluorometer. So this is the basic understanding of the fluorescence spectroscopy. And what is the principle? It is a very simple principle. I just explain you simply. When any molecule get the photon of a higher state, it go to the higher state, and when it come back to the ground state, there is a relaxation. This relaxation is in the form of loss of energy, emission of light, and this is simply called as the fluorescence, and normally we measure this. So if you look here, the fluorescence is an emission phenomenon. So it means there will be an emission where an energy transition from higher to lower state is accompanied by the radiation, and only the molecules which are in the excited form because of these photon, they are emit fluorescence, and once they can brought into the ground state, and they can emit the fluorescence. And measurement of this is simply the fluorescence spectroscopy. So again, I just try to explain the same thing. One thing you need to remember in the fluorescence spectroscopy, there are the two important aspects. One is called as the Stokes shift, and one is called the Jablonski diagram. So if you look here, it's nothing extraordinary again. So when any ultraviolet light or the beam of light excites the electron of the molecule of certain compound, it emits the light, and when it come back to the lower energy, there is a shift, and this shift is called as the Stokes shift. In a more simplified manner, if there is any molecule, when it accepts the electron and it go to the higher state, so it means there is an absorption spectra. It means these molecules absorb the light at a higher energy, and that is called as the absorption spectra. And as it reaches to the higher state, when it come back to the ground state, now there is a emission spectra, and there is a difference between this absorption spectra and the emission spectra, and this difference is simply called as the Stokes shift. So if you look here, so now you can see here, so imagine there is a molecule. If it absorbs a photon, it gains energy. It gains energy and enters into the excited state. One way, as I told you before, because this is a transition state, so one way for these molecules to return back to get relaxed is to emit a photon, and thus losing its energy. And when the emitted photon has a less energy than the absorbed photon, so in the beginning it is the absorbed photon which has a higher energy, it go to the higher state. When it return back to the lower state, the energy of the photon is lower, and this difference is called as the Stokes shift. You can simply here it is a wavelength during the absorption spectra. It's around like the UV light, and it's the wavelength around light, it's 350 to somewhere here. And when it releases the light, now the wavelength is a bit higher. So one is the absorption spectra and one is the emission spectra. The absorption spectra has a higher energy photon, and the emission spectra has a lower energy photon, and this difference is called as the Stokes shift, and it was given by like the Irish physicist George Gabriel Stokes. So what did it say? So Stokes difference is the difference between the position of the band maxima of the absorption and the emission spectra of the same electronic transition. It means the same molecule can absorb at the higher light. Because of this, it reaches to the excited state. When it back to the ground state, it releases the energy and it has a lower photon, and this difference is called as the Stokes shift. And this normally we use in the case of the molecular fluorescence. So as I told you before, it is simply the measurement of excitation wavelength and measuring the emission at a longer wavelength is called as the basically is the theory of the molecular fluorescence. It means in the beginning the wavelength is lower because it has a high energy. When it returns back to the ground state, it has a lower energy and the wavelength is higher. So this difference is normally we measure in the molecular fluorescence. There are the certain compounds that normally used for this the fluorescence. So one of the most the important compound is called the quinine, and it was long reported back in 1845. And now you can, this quinine is excited. It means it will receive a high photon by the ultraviolet light from the sun, and when it returns to the ground state, the quinine emits the blue light and with a wavelength of 450 nanometer. So if you look here, so when it is the excitation, it's around like 350 nanometer. It's like in the UV range. Once it returns to the ground state, now you can see here, this is the excitation spectra or the absorption spectra, and now here is the emission spectra, and here in the emission spectra now it releases the light of a longer wavelength and lower energy, as it said around 450 nanometer, and simply it is the blue light. So it is a very simple manner. Again, I try to explain that when any molecule, the fluorescence molecule, are excited by the photon or the high energy, it moves from the higher state to the ground state. During this transition there is a release of energy, and this is called as the fluorescence. And there is a difference in the absorption spectra. So first is the absorption spectra, and when it returns to the ground state there is an emission spectra, and the difference between these two are called as the Stokes shift. The same story as I told you before. So when any molecule is excited, when it returns to the ground state, this is called as the relaxation process. And this relaxation process could be monitored, could be captured, and could be measured in the form of fluorescence, phosphorence, vibrational relaxation, internal conversion of energy, external conversion, intersystem process. So these are the different mechanisms of the fluorescence, but mostly here if we talk about the fluorescence, mostly it is the release of energy. Sometimes there is also the vibrational relaxation, internal conversion, and the external. And it is this Jablonski diagram is nothing extraordinary. It is simply the representation of the relaxation process of this excitation. So imagine here, so this is the ground state, this is the excited state. So now there is the absorption spectra, it move here. When there is a vibrational relaxation, it returns to the lower state. During the internal conversion, again there is a relaxation of the lower state. Now it returns to the lower state, and again in the most of the cases there is a relaxation process in the form of vibrational relaxation, internal conversion, the fluorescence, phosphorence, intersystem tossing, and all together is simply called as the Jablonski diagram. So Jablonski diagram is a simple representation of the relaxation process takes place when any molecule from the higher state move to the lower state, and this relaxation could be easily measured in the form of vibrational relaxation, fluorescence, phosphorence, and the representation of this is called as Jablonski diagram. So definitely try to remember these two, the parameter when we talk about the fluorescence spectroscopy, spectrometry, what is the Stokes shift, this is very important, and also the Jablonski diagram. And for the instrumentation, I mean, as we discussed before, in the case of the normal spectrophotometry, so they have the source of the light, they have the cuvette, and they have the detector. And simply, I mean, they have the different kind of the filter, like we explain you in the fluorescence microscopy. They have the absorption, the filter, the emission filter. So if you look here, simply fluorescence have a means of analyzing the spectral distribution of the light emitted from the sample from the fluorescence emission spectrum, which may be by means of either variable interference, or you can simply use the monochromator, and then there is a measurement of the single beam of light. And moreover, in the case of some of the more advanced instrument, like the monochromators are attached, and these are provided for the detection or the selection of excitation and the analysis of the sample emission. In practice, if we want to consider the full potential of this technique, only a small band of emitted wavelength is examined and the incident light is not made excessive, just to minimize the possible photo decomposition. So we have to remember that we have to consider these parameters when we try to measure the fluorescence spectrophotometry. So this is a very, like a normal the representation. So you have the light source, then you have the excitation, and this excitation as the monochromator or the filter. Now you have the sample, and this sample definitely should have the capability or the capacity for the fluorescence. And normally, as I told you before, there are the number of the natural compound that can fluorescence. Sometime if we want to measure the concentration of certain protein, let's say imagine if they are tagged with GFP, YFP, they can also emit the fluorescence. They could be easily detected by the help of the fluorescence spectrophotometry. So now here is the sample, and now again here is the monochromator or the filter, and finally here there is a detector. So this is a very simplified way to represent the fluorescence spectrophotometry. And there are the different type of the light source. So mostly it is in the UV range, so it's the xenon, the mercury, and these are the different type of the monochromator, like the grading monochromator, and these are the different type of the detector. So again, the principle is the same as we discussed in the case of UV vis spectrophotometry. The only difference here is that the detection is in the form of the fluorescence, and this fluorescence could occur only when there is a high energy light is taken up by the sample. Because of this, they will reach to the excited state, and when they return back to the ground state, and there is a release of energy in the form of relaxation process, and you can simply measure. And these are the factor, because this is the transitions. You remember the concentration, if it is highly concentration, sometimes it's very difficult to detect. The structure of the molecule also play a very important role, the temperature on the solvent, and if there is any impurities in the solution, this will also affect your absorbance of this fluorescence spectrophotometry. So try to remember these points when you measure any fluorescence spectroscopy. And I think the final slide is there. I mean, there are the different type of the applications. It could be used in the drug. They can also carry out the test where the impurities, the binding of the drugs, the drug binding protein, some of this the target protein or the GFP binding protein. So there are the number of the application of this the fluorescence spectrophotometry. So I hope I try to make you understand that in the case of fluorescence spectrophotometry, we again is the same story, the spectral analysis and the measurement. The only difference is that we measure the fluorescence, and I try to explain you how the fluorescence came place, and there is a difference in terms of emission and the absorption spectra, and this difference is called the Stokes shift. And when you represent all the relaxation process for any molecule, when it moves from the ground state, when it moves from the excited state to the ground state, there is a different way of the relaxation process, and this could be easily represented in the form of Jablonski diagram. So I hope it is clear. So I will upload this slide on the YouTube. I will send you. So again, beat Corona, be safe, healthy, Jai Hind.